All right, let's get going here. Good morning, everyone. Let's see here. Okay, yep, let's get going. So today is the 27th. It's our second week of the semester here. We're all done with chapter one. So some of the homework assignments have already kind of come and gone. They're still open. You can still jump in there and do those assignments. So if you've fallen behind or if you just joined us, recently and you're just getting into the class, all those assignments should still be open until the time of the midterm. So that said, that the midterm will be here pretty soon. It should be so it'll open up next week on Wednesday, and it'll be open for 3 days, closing on Friday of next week, and that'll cover chapters one and two. We're going to start chapter two now, unless there's questions. Does anybody have any questions they want to go over? I'm happy to go through anything from the homework, any questions you have about the calendar, the schedule, the administrative stuff. Nothing? All right. Well, let's see. Let's think a little bit about what we've been doing. So in 1.3, we talked about sampling, right? And the goal with a sample is to make it look as much like the population as possible. We want to represent the population as much as possible. And so in 1.3, we talked about pitfalls, right? So it's important to understand things that can go wrong, common mistakes, so you can avoid them. You can plan for them and try to mitigate them, right? Then in 1.4, we actually talked about how to do sampling. And the key, if you have to, summarize it in one word, you would say randomness. We want to use randomness to make the process unbiased, right? And so in 1.4, we talked about randomness. We saw how to use a random number generator. And then we talked about the 5 common sampling methods, right? So that's where we're at. That's what we finished. Let's see. So, so Devin's asking about the exam. The exam will be a paper exam, paper and pencil exam that's administered at the testing center. So yeah, there's no remote proctoring. So in the past, if you've used Proctorio for another class or something, that's not an option for our class. The math department decided against using Proctorio. So yeah, it has to be at the testing center. Now, if you live outside of, if you live far away from the testing center and you can't drive there, then you can get a remote proctor. So if you live next to a university or a college or even a library, they can sometimes proctor exams. So that information is in the orientation module. I'm happy to talk with you more about that through email or if you want to meet with me in Zoom. Okay. Anything else? Any other questions? I will later this week put an announcement on Canvas that will have some practice problems to help you kind of review for that exam. And I've got a recorded video of a review session I did with some students, and I'll give you that recorded video on Canvas so you can watch that as well to help prepare for the first exam. Okay, so if there's no other questions, we'll go ahead and get going here with chapter 2. So yeah, we finished 1.4, right? So we looked at these different types of sampling methods. Now we're going to jump over to page 29. Okay, so I think I've told you this before, but I'm wondering maybe if I forgot to tell you this. I think I told you, but there's 2 classes that are basically very similar here at the college. There's 1040, there's 1045. Okay, so you guys are 1040. The 1045 class is 1040 plus algebra. So in the lecture notes, we have algebra as well. That doesn't apply to our class, so that's why we're going to skip these pages of algebra here. So there's quite a few pages here of algebra that you can work on if you want, but it's not really part of our class. So in fact, I'm going to jump all the way down to page 29 here. So please do that along with me. Okay. And so what we're going to begin here in chapter 2 is categorical data. Okay, so remember, there's 2 types of data, broadly speaking. There is categorical and there's quantitative. Okay, so with quantitative, I think of that as any kind of data that came from counting something or measuring it with a ruler or weighing it on a scale. If it's one of those three, it's probably quantitative, and if it's not one of those three, it's probably categorical. Categorical means categories, so the data values are labels, um, right-handed, left-handed, what kind of car you drive, stuff like that. These are categories. Okay, and so in chapter 2, we're going to go down this track here. Okay, we're going to come back to quantitative in chapter 4. So now here in chapter 2 and 3, we're mostly going to focus in on categorical data. So how do we work with it? What do we do with it? Where does it come from? How do we collect it? Stuff like that. Okay, so when we're working with categorical data, we have tables that we use. We have graphics, and we have statistics. Okay, so so we have tables, graphics, and statistics. Okay, so a statistic, of course, is a numerical summary, right? A graphic is a picture, some kind of picture, and then a table, imagine like a spreadsheet with columns and rows in it, right? So pretty much all of categorical data analysis begins with this table called the frequency table. So frequency in stats is another name for count. Okay, so it's basically a count table. And what we do for a single variable is we have the variable in a column, and then in the second column, we have the number of observational units that have that particular value of the variable. Okay, so earlier we did eye color. Let's switch over to hair color. It's another variable that's pretty easy to collect and easy to work with. So in the chat, if you would put in your hair color at birth, and we can have others down here, but basically, most people either have blonde hair or black hair or brown hair or red hair. But if you're other, then we can put in some others as well. It's perfectly fine. So if you're willing to participate, just put the hair color over in the chat, and we'll start collecting the data. Okay, so let's see, I have brown here. Let's see what the rest of you guys have. So yeah, just keep those coming. I'm gonna pick them up in the chat, and feel free to double check me as I collect the data. Okay, so let's see, we have brown, blonde, brown. Okay, I think I have everybody. Okay, so I've just done tick marks over here on the left, and then so we can count those up. So there were 4 with blonde, 3 with black, and then 10 with brown. And I'm not seeing anybody who had red hair. So yeah, good. So what is that? That's our frequency table. There it is. It's right there in front of us. Okay, so hair color is categorical, right? And then so we have the common levels for that, the common categories for hair color, right? And then we have a count of the number of times each of those occurred, right? So from that, we can count up the total number that participated. So we have 10 plus 3 plus 4, that's 17 in the sample. Okay, so lowercase n is our our letter that tells us the sample size. So there we go. All right, so, and that's where it all begins, is with this frequency table. And from there, we can do other things. We can get some numerical summaries here. So the first one, and the most important for sure when it comes to categorical data, is the proportion. So proportion is where you take is basically like a percentage, but it's written in a decimal value, right? So for example, what proportion of our class had blonde or brown hair at birth? So this or functions kind of like a plus. So we're going to take all the people with blonde hair, there were 4, plus all the people with brown hair, which is 10, and we're going to divide that by 17. Okay, so that's the proportion of people who had blonde or brown hair at birth. So we're going to go, let's see here. So that'll be 14 divided by 17. So that, a strong majority had blonde or brown at birth. So let's see, what was that? 0.824. What do we round to? There's not really a golden rule about rounding. So in the homework on exams, just look carefully at the directions. If they say round to 3 decimal places, do 3. If they say 20, do 20, right? Okay, so 0.824. What percent had blonde or brown hair at birth? Well, you know how proportions work, right? If you want to go from a proportion to a percentage, we attach the percentage symbol, and then we move the decimal place 2 units to the right. So that's 82.4% with those with blonde or brown hair at birth. Okay. What I find, what's better, percentages or proportions? Well, they're both very good. If I'm reporting results to somebody, I would probably use a percentage. If I'm doing mathematical arithmetic calculations, I would usually use a proportion. Okay. Great. Any questions there? So that's, nothing too, too complicated here. It's we're just adding and doing some division and creating a pretty basic table. But from that basic table, we can get a really good idea of what's going on with our sample or with our population, whatever it is that we're looking at here. From there, we'll put together a relative frequency table. And the relative frequency, well, relative to what? Well, 10 might not sound like a lot, but if there's only 17 in the sample, that's a lot, right? So we like the raw frequency, the raw count. That's very useful, but it's also useful to compare it to the total number that we have. So for example, for the blonde, there were 4 out of 17. Okay, so if we go 4 divided by 17, that's telling us about a quarter of the folks here were born with blonde hair. So what is that, 0.235? Okay, so the relative frequency, 0.235. You can write that as a percentage or as a proportion if you'd like. So I'd like you guys to do these other 3 quickly. For the next one there, that would be 3 out of 17, and then you guys do the rest, okay? So go ahead and calculate the relative frequency for black and brown there. And if you would, put that in the chat, and we'll just keep going, okay? So this is the beginnings of how we work with this really important type of data, the categorical data. Can anybody tell me some of these numbers? What's going to go? Okay, so for the next one here, we have about 18%, 0.176. And then for the brown, anybody have that? Is that pretty clear how we got black there? So we go 3 divided by 17. Good. Yep. So that's correct. And then Brock has the last one there. So for the third group, we have 10 divided by 17, and we get a pretty strong majority there, 0.588. Okay. And with the relative frequency, if you want to use percentages there, that's perfectly fine. And then there was nobody with red hair. What do we get when we add these all up? Earlier, when we added up this column, we got 17, which is the total number in the sample. Now, when we add these up, we're going to get something that's pretty close to 1. okay? And that's because 1 is 100%, right? So if you add up all of the categories there, it's got to be 100% or at least close to 100%. It might not be exactly 1 because of rounding, but you know, it shouldn't be too far off of 1. So if you get 0.998 or 0.997 or something, it's probably fine. It's just because of rounding, you didn't get quite 1. But if you get 0.75, you know, there's some kind of mistake that was made, and it's very easy to do that. So it's a nice little check you can do with your table to give you a good indication about whether or not you're correct, right? Okay, so that's our first thing we do with categorical data. We look at the table, the frequency table, and the relative frequency table. Okay, so the two tables, I mean, they're very closely related to each other. Then we move into some graphics. Okay, and some of these graphics are going to be easy. You'll have seen them already. Actually, others will be a little bit more complicated. So we'll move kind of quickly through some of them, and then on others we'll go a little bit more slowly. Okay, so what is the first graphic we see? The bar plot. Okay, so the bar plot, it's a common way to display a single categorical variable where the categories of the variable are on one axis and counts or proportions are on the other axis. So here we have frequency. Okay, so for blonde there were 4, so 4 is a little bit less than 5. So we'll have 1 bar here above blonde. Okay, and then for the next category there, black, we had 3. So 3 is a little bit less than 4. Okay, and so notice those two bars should have the same width to them. Okay, and then for brown, let's see how many were there in that category. There were 10. So we're going to have a taller bar there going up to 10. And notice that each bar is the same width, although the height can change for sure. Right, and then we just shade that in nicely. And none for red. Right, so it's a 0 there for the red. Notice we have spaces between the bars. The spaces there just emphasize the fact that this is categorical. Okay, that horizontal axis isn't a number line. We have categories there, and it'll become more relevant when we get to quantitative data, to our histogram, why we want to have spaces for the bar plot, but no spaces for the histogram. Okay, so just be aware that we want to have little spaces there, indicating and emphasizing the fact that we have a bar plot. Okay, so any questions there so far about categorical data? Not too bad, right? Okay. So, you know, look at this bar plot I've drawn. It's okay. Oh, by the way, don't forget your title. So let's see, this would be maybe hair color at birth. Okay. So always put a title on your graphs. It's just expected that you'll do that. Label the axes and should be good. Okay. So, but you know, so it's okay drawing it by hand, but you know, professional reports, reports that you would do for work, they're not going to be drawn by hand typically, right? You're going to put them into software and use the software graphs. Yeah. So same for us. We want to get comfortable using software here. If you're already good in Excel and you want to stick with Excel, great, do it. Just stick with Excel and you'll be fine this semester. Or if you have some other kind of software you like to use, that's great. But you know, if you don't, then I'd highly recommend you use GeoGebra. Okay, so I think we looked at GeoGebra last time for the random number generator. Let's go ahead and pull it up again and see how it works for bar plots. Okay, so we have the directions here, so you can read these directions here if you'd like. We have a video on Canvas. Let me just remind everybody of our videos. So let's see here. So on the home page, we have this link here to the YouTube channel. And there's a playlist here for GeoGebra. Okay, so this is the video we made for the for the GeoGebra, right? So there you go. So you can watch that video later if you need to. So how does it work? Well, we need a data set here to practice with. So if you look at this data set, this is looking at beverage size. And so, this is an important kind of data set for a restaurant or, one of these large fast food chains trying to understand what their customers are buying, right? And so every drink is typically going to be small or medium or large or extra large. Okay, I mean that's the vast majority, right, of the drink sizes. And so what this is it's a raw data set of orders by customers, right? So this customer here ordered an extra large beverage. This customer here ordered a medium, right, size beverage. This customer small. Okay, and so that is categorical data, right? And so to help, a graphic that, a very common graphic to begin with would be the bar plot. So how do we do the bar plot in GeoGebra? Well, let's go ahead and pull up GeoGebra. And again, remember, I think I've told you this, that there's lots and lots of different GeoGebra products. You can download it to your computer if you want, but I highly recommend just using their website version. It kind of depends on what device you have, I guess. But anyway, I've put it over there in the chat, this link. If you're using the internet browser version, make sure it says classic in the URL. If it doesn't say classic, then it's probably just going to end up being a big headache for you. Okay, so click on that one, and let's move over here and give this a try. So to get data into GeoGebra, you're going to have to get to the spreadsheet. Okay, so you see that spreadsheet there? So to do that, you hit this toggle and until you get the 3 dots, then you hit the 3 dots and you're going to come down here to spreadsheet. Okay, and then with the spreadsheet, that's where we're going to put in the drink sizes. Now, one thing about GeoGebra, it doesn't do super well with labels for categorical data. So we're going to have to switch it over to numbers. So it's still categorical, but instead of using names for labels for the categories, we're going to use numbers. Okay, so small is going to be a 1. Medium, we're going to code as 2. Large, we're going to code as 3. And extra large will be a 4. Okay, so in my data set, we could write that as a 1, a 2, a 4, 2. Like that. Does this make sense? And so it's not quantitative. These aren't like counts. They're just, it's like a code that we use for each category. Okay, so I'm going to come over here to the spreadsheet. I'm going to put the numbers in. Okay, and it looks like we have 20. Please let me know if I miss any of the numbers. It's really easy to do that. Okay, so we put the numbers into column A, and we're ready to go. I'll give you a minute to catch up if you're trying to do this along with me. Okay. Now, a common mistake people will make at this point is to forget to highlight the data. So you need to highlight the data. If you don't highlight the data at this point, it doesn't know what to use. Okay, so I'm going to come up here to A1 and I'm going to click on A1. Okay, so it goes blue, light blue. Then I'm going to click on it again and I'm going to hold it, and then still with the with the mouse held down, I'm going to drag down to the bottom. So when I get to the bottom, then I'm going to let go of the button on the mouse, and that column is highlighted. So now it knows what data set to use. Okay. Oh, oops, I messed that up. Darn it. Okay, what was that? That was a 1. All right, let me do that again. Okay, so again, we click on 1, we hold the button down, we go all the way to the bottom, then we let off, and now it's highlighted. Then from there, I'm going to come over here to this bar chart looking symbol. I'm going to hit this, and I'm going to go to one variable analysis. Okay, so this is one variable because, typically you get one drink when you are at a fast food restaurant. You can get more, but, if it's your order, then, you've got one size, right? Every drink is going to have one size, right? You can't have a drink that's both a medium and an extra large, right? So we click the one variable analysis, and this still isn't quite right. This isn't a histogram. Histogram is for quantitative data. So I'm going to come over here to this drop down, and I'm going to hit bar chart. And that's actually it right there. Okay. And what is it telling us? It's telling us that, well, this column here that's labeled 3 is by far the most common beverage chosen. The extra large is the least common. Medium is the second most common, and then the small is fairly rare, but more than extra large, right? So definitely, your customers are most interested in the medium and the large sizes there. Okay. By the way, on the project, you're going to have to occasionally produce graphs. So what I recommend doing is doing the graphs in GeoGebra and then using a screen copy tool. So my favorite is this thing called Snipping Tool. And so if you open up the Snipping Tool, you can take a screenshot easily of your chart. Then it's a JPEG file, an image file, and you can save that or copy it, whatever you want to do with it, and put it right into a Word document like that. Okay, or you can put it into Paint, another software program, and you can adjust, the title, the axes, you can update the appearance of the graph a little bit. Okay, so that's one of my favorite ways of producing a report, a statistical kind of report that looks professional. Okay, and so anyway, just a little aside there about that. The screenshot tool is nice. There's also a way of downloading this, so you can copy this to to your computer. There's lots of ways of doing it. Okay, so anyway, that's how we get the bar plot. Are there any questions about that? Does anybody want to see that again? I can go through it
Yeah, could you
again.
show the bar plot again? Just the
Yeah,
process of
you
getting
bet.
it.
You bet. You bet. Let's see. Let's actually just kind of take it from the beginning here. This is one reason I like the internet version, the browser version. Every now and then you get so much stuff in GeoGebra. It's just kind of nice to clear it all out and start from scratch. And it's just so much easier in the browser. You just hit the refresh. And so we go to the toggle, we hit the 3 dots, we go to spreadsheet, and then we have to put the data into A1. Okay, so I'm going to go Control V because I've already copied the data, and it just makes it easy to get data into the spreadsheet. So if you know about those kinds of commands, you can speed things up. So Control C copies numbers and and data. Control V pastes what you've already copied. Okay. All right. So we highlight the data. Then we're going to go over to the bar chart looking diagram here button, and we're going to go down to one variable analysis, right? Because a drink only has one size. You can't have a drink that has two sizes. Then we go to the drop down. Okay, histogram is not right. This is not a histogram. This is a bar chart. Okay, and notice there's spaces between the columns, like I was saying earlier, for bar charts. It emphasizes the fact that this is categorical data. This is not quantitative data. Okay, anything else or any other questions about that? I can go through that again if you like. It's pretty straightforward, I think. I mean, it's easy for me to do that.
Thank you.
You bet. All right. What else do we have? Well, the bar chart is really it's the most commonly used graphic for categorical data, but there is another one that's commonly used. I want to throw some shade at this, I guess you could say. The pie chart, it is commonly used, but it's not quite as good as the bar chart. So you will see it is commonly used by like newspapers, and you'll even see it in some scientific papers. But most statisticians kind of try to avoid the pie chart a little bit for reasons that we'll discuss in a little bit. But I do want to mention it. It's a well-known way to display a single categorical variable. Um, and so we'll look at the pie chart. Then the last thing I want to do here with these graphics is look at problems with graphics, right? So the bar chart is what we want to do, and then we want to talk about what we don't want to do. Okay, so we don't want to mislead people with our graphs, and we don't want to mislead ourselves either. Okay, so you don't want to mislead other people if you're doing research, and then if you're looking and reading research that was done by others, you don't want to be misled yourself, right? So we're going to look at what are called the misleading graphics, things that can go wrong and either intentionally or unintentionally confuse people. So the misleading graphics, these are graphics that deceive the reader into interpreting the data incorrectly. So what are some common misleading graphics? Well, we're going to look at three. We're going to look at the non-zero starting point. We're going to look at using two-dimensional pictures to depict a single variable, and then we're going to look at three-dimensional graphics. Okay. So example, we have home sales from 2 different months. So this might be home sales for, a small town. And in January, there were 25 homes sold, or 24. Then in April, it was about double. It was a little bit more than double. It went from 24 up to 50. What's wrong with this graphic? I mean, it's actually kind of a good-looking graphic, right? I mean, at first glance, it looks fine, right? It's certainly the kind of thing you would see in a newspaper, right? If you're reading about um, the housing market, right? It's kind of a big topic right now. So what's the problem with this? The problem is it's a one variable, uh, it's single variable data, but the picture that we're using is two-dimensional, right? Do you guys see this? I mean, the house has two dimensions, right? The house picture here has a length and a width, so it's a two-dimensional picture, but we have a one-dimensional variable. Okay, so why is the variable one-dimensional? Well, the number of houses sold is one variable, right? In a single month, you can't sell 26 houses and 36 houses, right? You can only sell one number of houses in a month, right? Typically, right? So what's the problem here? Why does it create problems? Well, I can prove to you that this picture here is only about a fourth the size of this picture over here. Why is that a problem? Well, what's 50 divided by 24? It's about 2, right? If I go 50 divided by 24, it's about 2.08. Okay, so if we just round to the nearest whole number, that's about 2. So the housing sales doubled from January to April. But if we look at this picture, it's actually about 4 times larger than the other one. Okay, so the amount doubled, but the picture size quadrupled. And that's a problem. Okay, I mean, the eyes can kind of be deceived here, right? You can look at that and, it looks quite exaggerated. And so why is that? Why does going from one dimension to two dimensions, why does it cause something that doubled to actually look like it quadrupled? Well, it's because of the fact that we have two dimensions. Okay, so both dimensions are doubling. That creates a quadrupling effect for the overall picture. Let me use a graphic over here. Let's say we have a square that's a 1 by 1 square. Okay, and then let's say we have another square that's a 2 by 2 square. Okay, so this is 2 by 2. So 2 is twice 1, right? So the one side doubled. what happened to the area? Well, area of a square is length times width, side squared, right? So the area here is 1. The area over here is 2 times 2, which is 4. Do you see how the area quadrupled? It went from 1 up to 4. Okay, and that's a big problem. Okay, it's going to create, or it can create an impression among the readers that the housing sales have really, really exploded. I mean, they did double, but they didn't quadruple, right? Does that make sense? So it's because of the two-dimensional nature here. Okay, so that's a big problem, and that's something that we want to avoid. So, so professional statisticians and data analysts and data scientists and analysts in general, they do try to avoid as much as possible using two-dimensional pictures for single variable data. Okay. What else? The non-zero starting point fools a lot of people. Okay, so we want to. It's not like we don't want to use it, but when we do use it, we want to be careful with it. We don't want to confuse ourselves, and we don't want to confuse our readers. Okay, so what's the problem? Well, let's look at this graphic here. So this graphic is good. They're using a bar chart, which we like, but they are but still there's something a little bit deceiving here with this graphic. So what is it? Well, this is the population of Winnipeg, right? So this is a city in Canada, and in 2013 the population was just under 700,000. Okay, in 2015 the population's increased. Okay, so if I bring this over to here, right? So here's the 2013 numbers. The 2013 is about right here, right? Well, in 2015, it looks like it's twice that, right? So, if you're not careful, if you're just kind of casually, looking at this graph, it almost looks like the population has doubled, but it's not doubled at all. It has increased, but what is the population in 2015? It's just over 715,000, right? It's about 717,000 or so, right? So it went from just under 700,000 to just a little bit more than 700,000. Okay, so it definitely didn't double. Why does it kind of look like it doubled? It's because the y-axis here does not begin at 0. Okay, the y-axis begins at 685,000. And so basically, if we were to zoom out, if we were to start this at 0, we would get an effect that looks more like this. Okay, so if it started actually at 0 like it's supposed to, the effect would be quite less impressive, right? And so basically by not starting at 0 like we've done here, it's zooming in on the very tops of the peaks of those bars, and it creates this kind of exaggerated looking effect. Now, that said, if you do start at 0, then what it can do is it can make it hard to see differences. Okay, so it's something we can't always avoid, basically. So what we do is we say, okay, just make sure that you realize that this does not start at 0. Okay, so we'll still make graphics like this, but we want to call out to the reader. We want to explain to the reader that this does not start at 0. And so and when you're producing a report, you'll want to explain that depending on your audience. And then also, especially when you're reading research, you'll look for that, right? So anytime you see a bar chart on the news or in a newspaper or in some report that you're reading, you'll want to look right away at that y-axis, and then you can kind of, you'll know what's going on a little bit more clearly, right? Does that make sense? So those are two things that can be misleading. So there's that. And then the last thing we want to talk about is this three-dimensional pie chart. Okay, these are really terrible, and well, I don't want to go overboard with it, but please avoid the three-dimensional pie charts as much as you can. These can be really deceptive. For example, here we have categorical data where we have 4 categories: item A, B, C, and D. So it's probably like sales, volume maybe for these 4 different items. And what's the problem here? Well, items in the foreground are exaggerated. Items in the background are minimized. Item C here is 5%. Item A back here is 11%. And 11 is twice 5, right? Or more, it's more than twice as large as 5. But you can tell that that slice in the back there just looks much smaller than the slice in front. Okay, and this is not a minor thing at all. These sorts of kind of tricky, tricky effects are used quite a bit. Unfortunately, there are people that are, basically trying to trick you at least a little bit from time to time. They're trying to sell you something, or just, they're trying to convince you of something, and it's something to be aware of. Okay, so anytime you see a three-dimensional pie chart, beware. And also, please don't use these yourselves. Okay, I know there is a sort of an aesthetic appeal to them, I admit, but they're just not good practice, really. Okay, so those are 3 common things I want you to look out for. The non-zero starting point, using 2-dimensional pictures to depict a single variable, and definitely we don't want to use 3-dimensional graphs. What do you guys think? Any questions there about that? Okay, so that's what we don't want to do. Let's look at this class activity here. I can't really get all 3 pictures on one screen, but what it is it's the same data set depicted 3 times. And what it is it's the population for each of the states in the US. So there's 50 states, right? And each state has a number of people that live in it. And what we've done is and that's categorical, right? I mean, there's 50 states. Each state is a category. And then we have a count of the number of people in each one. Okay. And then so we've depicted it as a pie chart. Then we've depicted it as a bar chart. And then we've depicted it as another bar chart, but notice that each column is shorter than the one that came before it. Okay, so it's in descending order, right? So it's descending as we go from left to right. When we put a bar chart in order, either descending or ascending, we call it a Pareto chart. Okay, so it's a bar chart, but since the columns are in order, we call it a Pareto chart. Okay, it's named after an Italian economist. Okay, so let me go quiet here for a couple minutes, and I'd like you to consider each of these 3 graphics. Okay, and I'm going to set up some rooms here. These breakout rooms, sometimes they work well, sometimes not so well, but I'm going to go ahead and open up 3 breakout rooms, and if you'd like, you can jump in and discuss these with other people. It's kind of nice, I think, to sometimes to chat with the other students, and it makes it a little bit more like a in-class, face-to-face class. But sometimes I can kind of find that I overdo these breakout rooms. So anyway, I'm going to open up the breakout rooms. We'll come back in about 5 minutes at 12:19 and discuss the relative strengths and weaknesses, the advantages and disadvantages of the 3 ways of depicting this data. Okay. Okay, so help me out here. So who can tell me something about the pie chart? Did you like it? Did you dislike it? Um, Maybe definitely tell me something bad about the pie chart, and then if there's something good about it, you can tell me that too. Anybody? Just maybe unmute yourself and
Well,
yeah,
I was a fan of the pie chart, but the people I was talking with did not like it because some of the titles can be kind of hard to read in the
yeah.
pie chart, but I liked it because it's very visually representative.
Yeah, I mean it is kind of it looks nice, right? It's got all these colors. It's kind of attractive, and in a way, you can kind of tell. Yeah, I mean, California, this is pretty clearly the largest state, and you can kind of tell. Yeah, Texas is probably the second largest. Illinois is quite large. Florida, and then is that New York down there, I believe. So, you can extract some information here, but beyond that, it's quite difficult, right? I mean, how do you compare, say, Arkansas to Utah, right? I mean, it's just it's quite inexact at this point, right? So it gives us some nice information, I think, at the beginning, but then the rest, it's not as useful. So it's really hard to compare state to state, right? So uh, after you get past the big 3 or 4 states. So it's hard to compare state to state. Let's see. What about the bar plot here? What was nice about the bar plot? What can, why do we like? I mean, I've already told you I prefer the bar plot here. What's nice about this one? All right, let's see here. So in the chat, it's simple and easy to read. Yeah, I mean, because it's in alphabetical order, you can very quickly find your state, right? So, or whatever state you're interested in. So, Utah here, we can see very clearly what the population of Utah is, or if you live in, Louisiana or any of these other states. Whereas up here, it might take you a while to find, the state that you're thinking about, right? Yeah, so the alphabetical is quite nice. It allows us to find things quickly. That's why we use alphabetical order in a lot of things, right? Is for helping us find things. The Pareto chart is nice. It's not in alphabetical order, and that makes it a little bit harder to find particular states, but it very clearly gives us an idea of the ranking of state size. Okay, so I don't think anybody would be surprised by California and Texas here, and maybe even Florida and New York. But it's kind of surprising to me that Pennsylvania has that many people in it. I mean, on second thought, I guess it does have lots of large cities there, but still, I just, it's not really in the front of my mind, Pennsylvania, very much. So anyway, it gives us a nice idea of state sizes there by population. That's the Pareto chart. Okay, so there we go. There are just some things to consider there with the graphics. And we're all done now with 2.1. We're ready to begin with inference. Okay, so any questions there about that? Let me draw a picture. It's a picture we've seen many times already. It's this graph here where we have our population, okay, with size capital N, and it's large enough so that we can't measure everybody or everything, right? So what we do is we take a sample using the techniques we discussed last time, right? So we have a sample of size little n, and we calculate a statistic from that sample, right? So we call that a statistic. So from our class, it might be the proportion of people who are born with brown hair. So let's go back a little bit. We have that data here. So about 59% of us were born with brown hair. That's a proportion. So 59% have brown hair, or at birth have brown hair, right? So that's a sample. So there is some true proportion of people in the whole population with brown hair, but we don't know what that is, right? This value, this unknown value, is called a parameter, right? So parameters go with population, statistics go with sample. So one of the big, so this step here is called descriptive statistics. Okay, so we're doing describing. So we're describing a sample. But this step over here, where we go from a statistic to make a statement about a parameter, is called inferential statistics. Okay, so we're going to make an inference about the whole population using our sample. Okay, so that process is called inference, and that's what we're going to begin here in chapter 2, in section 2.2. Okay, and it's definitely the more complicated. It's more complicated than descriptive statistics. Okay, so takes more time to talk about it. So so that's what we're going to begin here, and we actually jump down through a lot of algebra all the way down to page 40. So please join me here over on page 40, and we're going to begin by looking at a scientific study that was done. So this is section 2.2, and I'm also going to pull up our textbook. Okay, so if you look on page 22 of our textbook, there is a link to an article that appeared in the in the journal Nature. Okay, so if you follow science, news, you read science journalism, it's very likely you've heard of this journal before. It's probably the number one or number two kind of top journal in the world for general scientific papers. Okay, so they cover a wide range of topics, from astronomy to zoology, just kind of everything in between. Okay, very famous journal. And so anything that appears in Nature has been, carefully, researched and vetted and reviewed, right? And so this particular article, they were looking at this thing called behavioral asymmetry. What is behavioral asymmetry? Well, asymmetry is where one side is emphasized over another, right? And so you all know, I'm sure, that there are more right-handed people than left-handed people, okay? But why is that? I mean, if you look at the right hand and the left hand, as far as we can tell, right, just by appearance, they appear to be identical, right, in pretty much every way. Why is it that about what is the number? I think about 85% of people in the world are right-handed, about 15% are left-handed. Well, that is called behavioral asymmetry. Okay, and you read up on it. It's an interesting question. This guy was looking at other behavioral asymmetries. Okay, so it turns out that right-handedness is not limited to handedness. In fact, people tend to have a preferred foot, for example. So it turns out that more people are right-footed than left-footed for whatever reason. Okay, and people have a preference um, for just they tend to use one eye more than the other. It's really quite interesting why this is. Okay, despite appearing to be equal in both in every way, people do tend to have this preference for right-handedness and other kinds of behaviors for some reason. So what this guy was looking at is head turning. Okay, so if you come to this link here, they have the paper. This is actually a summary of the paper. And what is this? This is a statue over here of two people kissing. So what on earth is this about? So again, this is from the journal Nature. So this is a very serious paper. This is not like a silly paper or something. It's called head turning asymmetry. And so if you read this, what it talks about is uh, the fact that they know that during gestation, during pregnancy, the fetuses have a tendency, so babies, they have a tendency, a preference for turning their head to the right. How do they know this? Well, I suppose I figure it's probably because of all of the um, ultrasounds, right? So, I mean, most babies will have an ultrasound done, and I mean, they can just kind of count from these ultrasounds that if the baby has its head turned, tends to be to the right. Okay, so that's an established fact. He wasn't looking at this. What he was trying to figure out is if this behavioral asymmetry that's documented during gestation, during pregnancy, if that continues through adulthood. Okay, so in other words, with adults, we know that they have a preference. They tend to have a preference for right-handedness, or being right-handed. There's more right-handed people. Do people tend to turn their head to the right more than to the left if they have a choice? Okay, and that's what he was trying to figure out. So how do you go about testing something like this? Well, this is where the study gets pretty quirky and kind of fun and interesting. What he did is he went out and so if you read the study, he basically was in large public places with lots of people. So we're talking about airports, railway stations, beaches, and parks. And he was on three different continents. So he was in the U.S., he was in Germany, and he was in Turkey, right? So it's pretty wide sample there from across the world. Not every continent, but pretty nice broad sample. And so he watched 124 couples. Notice the lowercase n, that's our sample size. And he watched them kiss. So I know it sounds kind of weird, but what does kissing have to do with head turning? Well, think about it. When people go in to kiss, they tend to turn their head one way or the other, right? Because they don't want to bump noses. Yeah. Okay. So if you look at this picture carefully, you can tell that both of the people in this picture turn their head to the right. And over here, both of the people turn their head to the left to kiss. Okay. And so that's how he got his data set. Okay. And again, this was in the journal Nature. So this isn't like a silly data set. I know it seems kind of quirky and funny, but it was considered a good study that was done. So does this make sense? Any questions about that? So what happened when he did his observation? Well, out of 124 couples, 80 of them were turning their heads to the right. So out of 124 kisses, 80 were right turns. Okay, so that's a proportion of 0.645. Okay, all right. So 80 out of 124 of these kisses were turning to the right. So we have a proportion of about 65% for right turns. Okay. All right. So let's do a little discussion here of some vocabulary. Okay. So this is definitely categorical data, right? Because each kiss is either going to be a right turn or a left turn, right? Okay. So there's two categories. It's categorical. And so when we analyze categorical data, we tend to have one category that we're most interested in. Okay. Now, if you read the paper, he hypothesized that there was, even in adulthood, there was a lingering effect of a preference for right turns. Okay. And so the category he was most interested in was the right turn. Okay. So we called that category, it might sound like a kind of a weird name, but we call that category the success category. Okay. It doesn't mean that it's a good or a bad thing. What it means is that this is the category we are interested in. Okay. And we could very well call the other category success, but just because he hypothesized that the right turn is more common, it's just kind of more natural to call that the category of interest. So some symbols here. We need a proportion. Proportion begins with P, so P just makes sense here. But there's two proportions. There's a proportion that comes from a sample, and there's a proportion that comes from a population. So the proportion that comes from a sample is a statistic. And so to differentiate that from the parameter, we put a hat on it. Okay, so this is called p hat. That's how you say it, p hat, and it's a sample proportion. Okay, he didn't travel around the world and observe every single couple kissing, right? That's impossible. Um, he just looked at a sample, right? 124 or so, right? Okay, so it's a sample proportion. It's a statistic. Okay, so lowercase n again that's the sample size. So some definitions. Point estimate is the p hat. Okay, that's the value that estimates the true proportion of right turns out there. Okay. All right, so let's go back to the book for just a minute and link this in with what we were talking about earlier. Okay, so remember we have our 6-step process. We identify a question or a problem. So what was his question? Do couples have a preference for turning their heads to the right when kissing? So at first glance, it doesn't sound like a super important question to answer, but really underneath that, we're getting at something more important, which is behavioral asymmetry. Why do people, despite having a symmetric body plan, right? Why do they tend to prefer right to left, right? Then he designed a study and collected relevant data on the topic. Okay, so this is the author. I believe he's a professor at a German university. He might actually be Turkish, but I believe he lives in Europe. So the study is he observes 124 kissing couples and recorded the head turning behavior. Then we describe the data. Okay, so that's p hat. Okay, that's a proportion, right? So about 65% were right turns. Okay, and then we're going to do inference. Okay, so with the inference, we begin this topic called the hypothesis test. Okay, this is one of our major types of inference that we learn this semester, the hypothesis test. This technique, this statistical technique, is used in many different fields. Okay, in many different quantitative, driven fields. Okay, and so it's used in pharmaceuticals, it's used in biology, journal papers, physics, etc. Okay, it's widely used and respected technique. It is quite complicated though, so it's going to take a little while for us to digest it all. So let's define it. It's a statistical technique that's used to evaluate competing claims. This is competing claims using data. So what are the competing claims? Well, there's always two hypotheses. There is a null hypothesis and an alternative hypothesis. What does null mean? Null means nothing, right? Kind of nothing, all right? So it's the hypothesis of no effect. There's nothing really new or interesting to see here. It's kind of the status quo conservative hypothesis, okay? And so we call that H0, 0 for null, and it's the first of the two competing claims about the population value. And it typically takes a stance of no difference, no effect, nothing new or nothing interesting. It's the status quo, okay? The alternative hypothesis is the second competing claim, okay? And what is it competing with? The null hypothesis. So this is sort of the hypothesis of something new, and we often call it the researcher's hypothesis because that's what researchers are trying to do typically, right? If you're a researcher, you're trying to discover something new. You're not trying to prove something we already know, right? In astronomy, you don't get famous for proving that the Earth is round. We already know that, right? So researchers are typically trying to, you can think of it this way. They're sort of trying to kind of upset the status quo in a way, right? They're trying to prove something new or interesting, or trying to disprove something, kind of previous status quo knowledge, right? Okay, so what on earth are we doing here? Let's go ahead and put that into our head turning example. Okay, so there's a null and an alternative. So let me ask you guys, what would be more interesting? What would require further research? if there is a preference for turning to the right, or there's no preference for either side? What would be more interesting? I need somebody to answer that question for us. If you're a researcher, what would be more interesting and would require further research? That there is a preference for turning to the right, or that there's no preference at all? That there is a preference. Great. So you're exactly right. If there's a preference for turning to the right, then there's a mystery, right? There's something to follow up on, right? So that's going to be our alternative hypothesis. Okay, so the alternative researcher's hypothesis is that there is a preference for right turns. It's not that the researcher wants that to be the case. It's just that that's something kind of new. It's like a mystery that they're going to investigate. That's what scientists like to do. They like to, test things and investigate. So the null would be that there is no preference. Okay, no preference at all. Okay, so I was saying earlier that there are two letters here, right? There is the statistic, and then there's the parameter. They're both proportions. So p hat is the sample statistic, the sample proportion. P without the hat is the population proportion. Okay, so there's two different proportions here. There's the sample proportion, right? So that'd be like our 59% of us that are born with brown hair in this small sample from our class. Then P would be the true proportion among the entire population that are born with brown hair. Okay, so there's P hat, which comes from our sample, and we can measure it typically. And then there's P, which is at the population level, which is actually typically impossible to directly measure because nobody has a data set that has everybody's hair color in it, right? That's just impossible. Nobody has that, right? So what am I getting at? Well, when we write out the hypotheses, we use P. The hypothesis test is done at the population level. We're not testing a sample, we're testing out a claim about the entire population. Okay, so if there's no preference at all, what percentage of right turns would we get? Okay, so if you could observe every kiss in the world, I know it sounds ridiculous, but if you could, and people have no preference for right or left, what percentage of those would be right turns? Okay, so what is P? P is the population proportion of right turns. So if there's no preference, it would be 50-50. Exactly. Thank you, Armand. I'm going to write that as a proportion. You can write it as a percentage. It's fine. But doing mathematics, it's a little bit easier with proportions. So that's the null skeptics kind of conservative hypothesis of nothing new or interesting there. Okay. Until you prove to me that there's a preference for turning to the right, I'm not going to go around telling everybody that just because it sounds cool. I'm going to be skeptical, right? We like a certain level of skepticism, right? We don't want to jump on, we don't want to go around repeating things that sound interesting but are actually false, right? Okay, so we like to have some skepticism, so it's important to have the null hypothesis there. And so that's the null hypothesis, okay? So it's the skeptics' conservative hypothesis. What is the alternative here? Well, he was thinking that if you could observe everybody in the world, you would have more than 50% right turns. Okay, because he thinks that this effect from pregnancy, from gestation, actually continues on through life. Okay, so this is the alternative hypothesis, often called the researcher's hypothesis. So, what do you guys think? What does the data set say here? The data set is right at about 65%. 65% is not 50%. It is indeed more than 50%. So this data set is providing some evidence in favor of the alternative. Okay, so the data, his data, right, do provide evidence in favor of the alternative hypothesis. Okay, because it's more than 50%. But my question for you is, how strong is the evidence? Okay, imagine you're a researcher. Let's say you're a biologist and you're interested in this behavioral asymmetry. There's a lot of people who think about this for their careers. Um, would you publish a paper? Would you stake your reputation on this data set where it's 65%? I mean, you're probably only going to publish if you're convinced of it, right? How convincing is it to you, this 65%? You tell me, either in the chat or just say it out loud. Do you find this extremely convincing? Do you find it somewhat convincing, or do you find it not convincing at all? I'm curious. What do you think? Is 65% extremely strong evidence? Is it weak evidence, or is it somewhat strong? Brock says somewhat. We got a lot of somewhats in here. Everybody's saying somewhat. And I think that's the correct position at this point for you to take. That doesn't really seem like a huge difference, right? I mean, if we go 65% minus 50%, it's a 15% difference. Well, he still published this paper, and Nature still, accepted this paper for publication. So it turns out that this is extremely strong evidence. Why? Okay, why is 15% extremely strong? Well, what we need is a way of testing this claim. Okay, we need a way of determining how strong the evidence is. The key is this thing called the p-value. Okay, so the p-value or probability value, we're going to talk about this on Wednesday or on Thursday, is going to quantify for us how strong the evidence is. Okay, so how do you go about finding out how strong the evidence is? Well, we are going to find something in the world that's 50-50. Okay, so what we're going to do is we're going to assume that there's no preference. We're going to assume that when he was out there in the field, every couple he looked at had a 50-50 chance of turning to the right. Okay, so we're going to assume that this 65% just came from chance. Okay, this 15% difference is just due to chance. We're going to assume that. And what we're going to do is we need to have some kind of process out there that's 50-50. Can anybody think of something in the world that has a 50-50 chance of happening and something that's easy for us to access? Any ideas out there? How about a coin flip? Exactly. Thank you, Killian. That's exactly what we're going to do. Okay, so we have 3 minutes. I just don't think there's any chance of us finishing this, but let's just kind of at least look at the coin flipping software. So there's a couple ways of doing this. One way is to go to Google and just look up flip a coin. Okay, so flipping a coin is a fairly common thing, right? I mean, we do it at sporting events. Gamblers are kind of doing something like this. So it turns out that this is actually something that's all over the internet. These little coin flipping things. The other option is to reach into your pocket and pull out a coin. So if you still have, I typically don't have many coins around, but if you've got a coin, you can pull out a coin and do this. But if you don't have a physical coin at hand, go ahead and go to Google and press flip a coin. And what we're going to do is we're basically going to see how likely it is with a 50-50 process. Okay, if we take a 50-50 process and we go through it 124 times, we're going to see how likely it is that we would get 80 heads, right? So, or 80 right turns. So what we're going to do is we're going to assign right turn to heads. Okay, so we're going to flip a coin. Here's our process, and we're going to have to do this on Wednesday. We're going to flip a coin 124 times. Okay, and we're going to assign heads to a right turn. If you want, you can do tails to a right turn. Doesn't really matter. It's all equivalent. But anyway, so we're going to say, all right, when the coin lands on heads, it's going to be considered a right turn, right? And we're going to do that 124 times. And we're going to see how likely it is to get 80 heads. Okay, so under the null hypothesis, it's 50-50. And so, we're pretty sure that when you flip a coin, it's about 50-50. So the coin flipping actually can be used as a way of measuring how likely it is to get 80 out of 124 if it's a 50-50 process. It's a very beautiful thing. It's called randomization. Okay, and it's commonly used in statistics at all levels, from intro stats all the way up to PhD level statistical research. Okay, so it's called randomization. And we're out of time for today, but that's what we'll start with on Wednesday. And we're going to see why his study was so convincing. They published it, and I'll just tell you the results. People do believe that adults have a tendency to turn their head to the right more than to the left. Okay, just like they tend to be more right-handed than left-handed. Okay, so I'll stop there. We're out of time. Any questions before we break for the day?
Could you show us page 40 of the PDF again?
You bet.
I just want to get the definitions for those.
The definitions? Okay, great. Is that good right there?
Yeah, thank you.
Okay, and then Sam is asking, where do we find the recorded Zoom lectures? So I'm going to let you write those definitions down, and then Sam, I'll try to show you over here in Zoom where to go. Your Zoom probably looks a little bit different than mine, but they should be in Zoom. So just tell me when you have all those definitions down, and then I'm going to navigate over to the Zoom meeting real quick. Thank you, guys.
All right, I got those. Thank you so
Good?
much.
All right, you bet. All right, so how do we